Hi, everyone. Thank you for joining us today. A special welcome to the VJUG members who are joining us. Today, I'm with Simon Ritter, Deputy CTO at Azul Systems. He'll be talking to us about the 10 reasons why Java is the best platform for developing IoT applications. If you have questions, don't hesitate. Ask us on Twitter, #VirtualIoT, or in the sidebar in YouTube. So Simon, without further ado.
Okay, thank you very much. Let me just go to screen here. Right, so hopefully you can now see my slides. Right, so the idea behind this presentation is really to talk about why Java is a great platform for developing applications for the Internet of Things. And when I sat down to put these slides together, I thought to myself, well, okay, the first thing we need to really understand is what do we actually mean by the Internet of Things in this particular context? And so really what we're talking about here is connected devices, so a network of things. And typically what we're going to see in terms of the networking that these devices are going to use is it's going to be familiar TCP/IP, and then there'll be some sort of messaging protocol layered on top of that. MQTT seems to be a very popular protocol that's used for Internet of Things type devices, but there are other options in terms of that. So there's some sort of messaging so that we can send messages with data from one device to another, one device to a gateway, from the gateway to the cloud, and so on. Really, the key thing when we're talking about Internet of Things is devices which aren't just dumb. They aren't just devices which are going to gather data and just pass that data on. It's really about having devices that have some kind of processing capability, some kind of ability to do something with the data before they pass it on. Now, that could be deciding what information is useful, so filtering out certain pieces of data and then passing those up the chain so that they can be acted on. Or it could be aggregating data, so taking a number of different values, producing some new value from that, and then passing that up the chain. But really the key thing is having the ability to process information at the end point rather than just passing it back. So a sensor doesn't do anything other than sending the information. What we're talking about here is smart devices that can actually do something with that information. And one of the key things about that is even though you have processing ability there, what you're dealing with is things that have very constrained resources. That could be low power CPU, it could be a small amount of memory, that could be a small amount of storage. Network connectivity could be the type of connectivity where it's not always continuous. So there could be certain times when you're able to connect to the network, but other times when you're not able to connect to the network. If you're dealing with remote systems, if it's in a field or if it's in a forest somewhere, there could be problems with network connectivity. So again, having a smart device that can cache information, and then when the network connectivity comes back again, it can send whatever's required, is a very useful thing to be able to do. And the other thing is because these devices could be placed anywhere, potentially power is going to be an issue. They may not be plugged in to a power outlet. They could well be running off batteries. They could be running off renewable energy sources, using solar power, that type of thing. So these are all the things that we're dealing with in terms of the Internet of Things. Now, if we look at how Java fits into that, really you can kind of say, well, if we look at the very smallest devices, the sort of micro units that we're dealing with here, where they've got very, very small processors, we're not really dealing with Java at that level because the amount of resources you have in terms of processing power and especially memory is just so low that you can't run a full standard Java environment on those devices. If you get down to, sort of kilobytes of memory, hundreds of kilobytes of memory, then you can't run a full Java SE environment on that. So there are some specialist solutions available in that case. So there's things like Java Card, which really does fit into the literally tens of kilobytes of memory. There's things like MicroEJ, which is a sort of a project that's looking at, again, shrinking the Java virtual machine down into a very small space. And there's the more well-known Java Micro Edition, which again sort of hits the hundreds of kilobytes as a minimum footprint for memory. So what we're going to talk about in this particular presentation is about Java SE. So the full Java that we're familiar with, the popular JVM, the language, the class libraries. So everything is the same as you would use in terms of developing applications that would run on a desktop, that would run in the cloud, that would run on servers. All of that is going to be exactly the same. What might not be quite the same is the way that the JVM works, but that doesn't matter, because in that case, what we're dealing with is more the implementation. From a development point of view, everything is the same. Same language, same bytecodes, but how those are interpreted in the JVM might be slightly different. But from a development point of view, you don't need to worry about that. In terms of the typical kind of IoT applications that we deal with in this sort of respect is some smart devices. Smart devices which do have enough power to run a full Java environment. But things like home automation, where you can plug things into an outlet, where you do have a bit more processing power, that kind of thing will run. Gateways as well is a very good example of where you can use Java to do a lot of interesting and complex things. Now, in terms of looking at Eclipse IoT with Java, what we're really saying here is, well, okay, at the bottom we've got lots of different types of hardware that people are using. And that's one of the key things I'll come to in a moment, is the ability to support lots of different types of hardware, different processors, different configurations, different interfaces, different sensors, all of those things. But then using Java to make that all appear to be the same. So it's kind of virtualization of the hardware from the point of view of the application code. Eclipse then adds some very useful projects. There's Kura, which is about taking a sort of Java and then using it to provide a machine-to-machine framework. The idea then is you can have not just machines to users, users to machines, but actually have machines connecting to machines and sending information from one another without any human interaction. So that's very much focused on that. Kind of things that you would see with that, things like vehicle monitoring, industrial equipment monitoring, those sorts of things. And that gives you a very powerful set of libraries to enable you to interact with the underlying hardware. So if you have got sensors that you need to access, then there's support for things like GPIO, things like I2C, which are familiar to embedded developers. The other side of that is Eclipse SmartHome. Again, this is a framework. Both of these use OSGI as a way of modularizing the application and the frameworks. And what Eclipse SmartHome does is try to give you a common way of developing things for home automation. So it includes things like a rules engine, it includes things like a declarative user interface and persistence management. So there's all sorts of things that you can use there in terms of developing IoT applications on top of Java, because Java gives you the basic layer, but then you need the libraries and the frameworks on top of that to address the needs specifically for IoT type applications. Right, so let's get into the 10 things which make Java the best platform for developing Internet of Things applications. And the first one is what I've called Moore's Law means more. And what I mean by that is that Java is a mature platform. It's been around now for 21 years. So in programming terms, it's not the oldest, but it's certainly not the youngest either. And that has a really powerful advantage because things have changed over those last 21 years. If you look at 1995, when Java was first released, and you looked at a typical desktop system that you might buy in those days, what you'd be looking at is something of the order of 8 megabytes of RAM and some sort of 32-bit processor. It would be typically a 486 from Intel or maybe a Pentium class processor running at maybe 100 megahertz, something a bit over 100 megahertz. And that would cost you about $1,500. Now, if you move forward 21 years, Moore's Law says that the processing power of computers doubles roughly every 18 months to 2 years. So if you say 2 years, then what we're looking at is effectively a 1,000-fold increase in the processing power that's available to us in machines today. The flip side of that is not only do we have far more power, it means that providing the same amount of processing power becomes exponentially cheaper as well. A good example of that is the Raspberry Pi. Now, Raspberry Pi started out, it must be about 4 years ago now. And when it first came out, everybody said, wow, this is incredible. We have a full computer with a gigabyte of memory, with a processor that runs at a gigahertz if you overclock the first ones. And it had video, it had networking, it had USB ports, all of that for $25. And everybody said, this is incredible. We have a processor and all these things for $25. And as we've seen over the last sort of year or so, the Raspberry Pi Foundation have gone even further with that. They took it as a challenge, and then they came out with the Raspberry Pi Zero. The Raspberry Pi Zero has 512 megabytes of RAM, so it's half of the memory that you get in the full Raspberry Pi. Still got an ARM processor that will clock at 1 gigahertz. Admittedly, it doesn't have the network interface, but you can do that through USB. It does have a video interface. It has video chip, connectivity for a camera, all those sorts of things. And that is $5. So you've got far more processing power than you would have had in a PC in 1995 in a board which costs retail $5. Imagine what that actually costs in terms of manufacturing. So the key point here is that we can take the sort of applications that we were running in 1995, and we can easily run those on the hardware that we have for embedded devices in 2016. And that includes Java. So Java was developed to run in machines that had 8 megabytes of memory and ran in a couple of hundred megahertz CPUs. Now, how much do you really need to run your application? And it's interesting because I looked at the sort of release documentation for Java SE 8, and this actually says that you need 128 megabytes of RAM to run the Java runtime. And rather quaintly, they also say that the minimum processor specification is a Pentium 2 running at 266 megahertz. So that's your minimum specification. So you might think, well, okay, so I just said that you could run the Java virtual machine in 8 megabytes of memory back in 1995, but now we need 128 megabytes of memory. Sure, it's still smaller than you get in a Raspberry Pi, but it's still quite a lot compared to some small embedded devices. So I did a bit more research on this, and I found out that if you really want to, you can actually squeeze it down to smaller. That's the recommendation from Oracle, 128 megabytes. If you use the -XMX option on your JVM when you start it up, you can control the maximum heap size for your JVM. And you can obviously turn that down as low as you want in theory. So I thought, okay, let's see how low I can actually get the JVM running. So I wrote myself a small application, didn't really do very much. It's really just a sort of idea of doing something which would occupy the JVM. And what I found is that I could kind of make the heap smaller and smaller, but ultimately I couldn't get the JVM to run in anything less than about 9.5 megabytes of memory. But that's still very good. I mean, 9.5, okay, it's a little bit more than 8, but it's still very, very small when you think about the amount of memory that embedded devices have today. So you can still take the full Java SE 8 and run it in less than 10 megabytes of memory. Sure, if you want to start using the libraries, then it's going to go up. The more libraries you use, the bigger it's going to get. But for a very basic application, you can get the size of the runtime environment down to a very small size. Second feature that I want to highlight is write once, run anywhere. And this is the catchphrase that's been used for Java right from the very beginning. The important thing here is not just that many people refer to it as write once, test everywhere, which is in a way is a very good thing to do. You should always test your code. But it does mean that you can take the same set of Java source code, compile it into bytecodes, and then have it run on any Java virtual machine that implements the full specification. That means that you as a developer, when you're developing IoT applications, when you're using different hardware for the devices that you're deploying to, don't have to worry about specifics of, am I using an ARM processor, or am I using an Intel processor, am I using MIPS, am I using PowerPC? All of that's hidden from you by this virtualization, as I mentioned earlier, of the machine, Java virtual machine, which takes care of all of that for you. And so the idea is you write your code to run on the Java virtual machine, and then you just put it wherever you want, whatever platform, whatever hardware is being used. Clearly, that's a big advantage because it means you're not continually porting application code from one platform to another. Once you've ported the JVM, and hopefully somebody does that for you, your application code can run wherever the JVM runs. Now, obviously, we need to look at some of the details of that, because when it comes to the idea of dynamic compilation, people obviously think that this has an impact on performance. So some people think Java is slow because it's interpreted. What happens is that the bytecodes are sort of a halfway between source code and fully compiled into native instructions. So when you start up your Java application, it has to take those bytecodes, convert them into the necessary native instructions for whichever platform it's on, and then run those native instructions to execute your application code. So people think Java is slow. Well, not anymore. You see, now we have adaptive compilation. I've had this for a long time in Java, actually, but people still have this sort of persistent idea that Java is slow, especially when you compare it to C and C++ applications. So what we do with adaptive compilation is we say, right, as the application runs, the JVM will monitor which methods are being called. When you start calling them in a loop and you do them a certain number of times, the Java virtual machine will compile that code into native instructions, cache that, so it doesn't have to do it every time the method is called. There are different compilers that can be used within the virtual machine. So there's typically the C1 and the C2 compiler, which have different profiles from the point of view of how fast they start up, so how fast they compile code, and then what level of optimization they reach. So C1 will start up faster, C2 will start up a bit slower, but will reach a higher level of optimum performance. The other thing about that is that in certain situations, Java code can outperform native code. Now you might think, well, how is that possible? But what the reason behind that is that you've actually got the ability in Java to do more with the JVM, to do more aggressive optimizations than you would with statically compiled code. Because Java is a dynamic language where you can use a class loader and you can load classes at runtime, if you try to do static compilation, you'll run into the problem of saying, well, okay, I think that's the method that's going to be called at that point, but because we could load a different class, we could hit a situation where the method that we would call is not the one that we think it's going to be. So we can't statically link that. With dynamic nature of compiling as the system runs, we know exactly which classes are loaded, so we know exactly which method will be called, and then we can optimize and inline that method as the code is compiled. There's a number of other optimizations that can be used once we have an exact knowledge of the classes that are loaded at runtime. Memory management is another thing that the JVM does for us. So the virtualization of the machine isn't just about dealing with compiling into bytecodes. It's also about making life easier for you as a developer. If you look at C and C++ as the sort of examples of languages that are used traditionally for developing embedded systems and therefore IoT systems, they have issues because you as a developer have to explicitly allocate space for the data or the objects that you're using. So you either use new in the case of C++, or you use malloc in the case of C. You allocate the space for your object or your data, and then you write the data into that. When you finish with it, you have to remember to deallocate that space. So you either have to delete the object in C++, or you have to free the space from your C application. Java makes your life simpler because it handles all the memory allocation and the deallocation automatically for you. We have this thing called the garbage collector, so that when you finish using objects, you no longer have references to them. The JVM will notice that because it does a sweep or it does an analysis of all the references in the system, and it'll say, okay, this object is no longer being used, it's no longer referenced, so it's eligible for collection. The garbage collector will then at some point say, okay, let's reuse that space, allocate a new object to it. So the idea here is that you can avoid many of the problems of memory leaks that you might get with C and C++ applications. Now, I'm not trying to say that you can't possibly have a memory leak in Java, because yes, you can. If you maintain a reference to an object that you don't actually need anymore, and you keep adding more and more references to objects, you can certainly have a memory leak because the garbage collector won't be able to collect objects if you still maintain references to them. But from the point of view of simple memory leaks, that problem goes away. Again, let's look at the way that this impacts performance. Now, some people think Java is slow because of the garbage collector. And so people think, well, you've got the garbage collector, that introduces non-deterministic behavior to my application because the garbage collector will start at times that suit the JVM. I don't know when that's going to be. I don't know how long the garbage collector will run for, how much impact it will have on my performance. Well, again, not so much anymore, because since the introduction of Java back in 1995, a lot of work has gone into improving the way that garbage collection works. We now use a thing called a generational heap space. This is based on what's called the weak generational hypothesis, which says that most objects, in fact, the vast majority of objects, are only used for a very, very short amount of time. If you put them in a young generation, they can be garbage collected from their very low cost, as compared with the old generation where they take a little bit more time and a bit more effort. So you can get very, very good performance from your garbage collector if all your objects are very short-lived. Similarly, because of the way that the allocation system works, we use pointer bumping to allocate space for objects in the young generation. The time it takes to allocate space for an object in Java is about 6 machine instructions. And that's way faster than if you're using something like malloc. So you can do very fast object allocation. Similarly, there's a choice of way to collect your objects when they're no longer required. So there's ideas behind parallel collection, there's ideas behind concurrent collection. So you can actually have parts of the garbage collection cycle running concurrently with your application code, again, to enable it to improve performance. Number 4 on our list, no explicit pointers. This was a big decision when Java was first being designed and then when it was first created, was not to have the same principle that you have in C and C++, where a reference to a piece of data is through an explicit memory address. So in C and C++, you have pointers. Pointers are actually memory addresses that you can manipulate. You can index through them, or you can manipulate those references to find data in different places. And that has some advantages in different places, but it also can have some real disadvantages. One of those is around the idea of security. The buffer overrun is a classic way of trying to defeat security systems, because you say, well, okay, I know that I have a particular array here of a particular size. I want to get some memory that I shouldn't really be able to get access to, but I'll do that by indexing off the end of the array, because I know what memory is going to be held there. And so I can access memory that I shouldn't really be able to access through doing that sort of thing. Java doesn't have the idea of explicit memory pointers, so you can't manipulate a pointer. If you have a reference to an object, that reference can't be changed arithmetically. You can't add something to it to change where it points to. You can only change that reference to a different object. All of that's controlled by the JVM. So it's very tight in terms of the security from the point of view of how you can manipulate memory pointers through the JVM. Java has security built in. So this idea of no explicit pointers is also related to the idea of security. So Java has a very secure model behind it. When it was first created, Java was designed to be run in a distributed environment. It was designed so that code could be moved around a network and run in different machines, which is great because it allows you more flexibility. But it was also designed such that that system couldn't be used to circumvent security measures. It couldn't be used to deploy viruses and those types of things. Often people look at Java and they say, well, you know, JDK 7, JDK 8 had quite a number of security issues. There's a lot in the press about this. Well, that's true, but almost entirely the problems that were JDK 7 and JDK 8 recently were to do with the browser plugin. And that's obviously nothing to do with the way that IoT applications work. You don't use the browser plugin. So a lot of these things had absolutely no impact on how IoT applications would work. Even if you look in more detail about how bytecodes are used, there's a 4-phase verification process of bytecodes when they're loaded into the JVM, so that you can't then start manipulating the bytecodes by hand, writing an editor and then trying to figure out a way of doing some malicious things through manipulating bytecodes. So you can't handcraft viruses that way. It's all checked by the JVM to make sure it's legitimate. Number 5, comprehensive libraries. This is one of the really great things about Java, is that when you want to do something, there's a huge number of class libraries supplied with the JDK. There's about 4,200 classes in the standard class libraries in JDK 8, which means you have a wonderful set of APIs that you can choose from. You don't have to write lists. You don't have to write SQL statements. You don't have to write read-write locks. All of those things are provided for you. But if that's not enough, there's a wealth of open source and commercial APIs available. If you can think of something, somebody's probably already written an API in Java that will do it for you. So when it comes to building applications, you can pull things from different places, whether it's commercial, whether it's open source, whether it's the standard class libraries, and bring all those things together so you can focus on getting the job done for your IoT application, rather than having to think about how to write all the basic libraries that you need for that application. And one of the ones I want to highlight on this is called the Device I/O project. This is being developed, open source project, through the OpenJDK project as well. And this is very much ideal for IoT projects. I mentioned earlier that with the Kura project from Eclipse, that gives you access to the underlying hardware. The Device I/O is about the same sort of idea. If you're running something on like a Raspberry Pi has a number of pins that you can connect different sensors, different actuators to, and you need some way of interacting with that. You need some programmatic way of controlling them. So the Device I/O project gives you all of the common interfacing techniques. There's GPIO, general purpose I/O, I2C, SPI, UART for serial communication. All of these things become very simple because there's just an API and you say, okay, open this pin as this type of connection, send this data, read data from there. All of it's very simple from a Java programming point of view. So it does make your life a lot easier. And as I say, there's a huge range of these types of APIs. So if you want to do things like Bluetooth, if you want to do things like USB connections, there's the ability to do that. GPS, there's libraries for that. Pretty much anything you can think of, as I say, there will be a library available for you, and many that are focused on the idea of IoT as opposed to enterprise Java. Number 6, multi-threading built in. This is very useful because, of course, as machines get more powerful, and even IoT type devices, you find that they are becoming multi-core. But that in itself isn't a reason for having multi-threading. Even with a single processor, multi-threading can be very useful, because the way that the operating system works is that you can do time sharing and you can get the illusion of having multiple cores, even if you only have one. But how you program that is the tricky bit. So if you're using other platforms, other programming languages, doing multi-threading can be quite hard. With Java, right from the very beginning, multi-threading was built into that, even to the point where in the early days of Java, you had certain platforms that didn't support the idea of threads in the operating system. And so the JVM would actually do that for you. There was a thing called green threads that would provide a layer that implemented a threading system on top of an operating system that didn't have the idea of threads. Now, in terms of the kind of way that you can do that, Java has really progressed over the years. So back in the beginning, there was the idea of the thread class. So you can start your own thread, you can have something execute separately in terms of the code that's working there. Then in JDK 5, the concurrency utilities were introduced to make life easier for writing cooperative multi-threaded code. We had things like semaphore, we had things like mutexes, we had things like read-write locks and atomic operations. All of these were introduced, which made the idea of moving data, having threads cooperate between themselves a lot easier. Java SE7, we had the fork join framework, which was another idea to improve the ability to write multi-threading code without having a lot of the complexity involved. Fork join framework allows you to take a big task that could be decomposed into smaller ones, have that happen recursively until we get to a small enough unit of work that can be allocated to a single thread. Framework takes care of all of the dealing with creating the thread pool, creating the queues, managing the queues for the jobs, and you don't have to do that. So you set up your framework, you set up your task, have it work in the thread pool, and then you get the result at the end. So it's a lot simpler in that sense. And then in JDK 8, we also had the introduction of parallel streams. Streams was introduced in JDK 8 to give us a more functional style of programming. Again, we can apply all of this to IoT because it's all available in Java SE. So it'll run on the Raspberry Pi, it'll run on anything that supports the full Java SE virtual machine. What we can then do is say, right, we want to take a collection of objects and we want to process that. And rather than doing it sequentially, we can simply say, right, create a parallel stream rather than a serial stream. And the fork join framework will be used underneath to make everything happen as parallel as can be done with the tasks that are being done by whatever code you've written. So there's a lot of simplification of dealing with multi-threading if you use Java, certainly compared to other platforms that you might be using for embedded programming. Number 7, flexible deployment. Now, as Java has become more mature, obviously more and more features have been added to the platform. Now, that's a good thing because now we don't have to write list classes, we don't have to write mutexes and things like that. But it does mean that the size of the standard class libraries has got bigger and bigger. So we started off with 200 class libraries in JDK 1.0. We've now got 4,200. So it's much, much bigger. And if you're trying to deploy that into a resource-constrained device, that can be an issue. Now, I said that you can run the JVM in a very small memory footprint. Obviously, the more libraries you use, the more space the JVM is going to take in terms of the runtime memory. But from the point of view of the deployment footprint as well, what's tried to do is to make that more flexible, make it more smaller, in effect, for applications that don't need everything. JDK 8 introduced the idea of compact profiles. What these were subsets of the full Java runtime class libraries. And in the diagram here, you can see that the full JRE class library is about 54 megabytes. Compact Profile 3 is 30, Compact Profile 2 is 16 megabytes, and Compact Profile 1 is a bit under 11 megabytes. And the idea is that each of those subsets has smaller sets of the standard class libraries. Compact Profile 1 has all of things like class loader, security manager, object, string, logging, things like that. Compact Profile 2 adds more features to that. Compact Profile 3 adds more features to that. But it's still a little restrictive in terms of the flexibility that you have for deploying your application. JDK 9, the big feature in that is going to be modularity. So now, rather than having one big jar file, rt.jar, that contains all of the libraries for Java, and even with compact profiles, you've still got big jar files for that. You'll have many smaller modules that you can then pick and choose which ones you want to build your application and reduce the size of the footprint of your application on that platform. One of the things that JDK 9 does for that is it provides you with a nice tool called jlink. What jlink will allow you to do is to build a full Java runtime for just your application. So you can say, okay, I want to take my application, which I've called com.azul.app, and I'm going to build a runtime, which is the Java virtual machine, the core modules that I need for my application, the modules I need for my own code for my application, and put everything into one image. So I'll output all of that. It will only have the base module, logging module, SQL, XML, app, Zoop, and Zeta. So only the modules that are needed for that application will be placed in the runtime. You can then deploy that onto your device, and you know that your application will run because all of the modules are there. But it will be a lot smaller than the runtime you would have if you took the full JRE, or even if you were using the compact profiles. Built-in remote management. This is another very important thing for IoT devices where they're going to be spread around a lot in places that might not be very accessible. What you want to do is you want to have the ability to manage those devices remotely. And we have the ability within Java to do that. We have a thing called JMX, the Java Management Extensions, so that you can actually say, right, I want to be able to manage my application or the JVM that the application is running on top of. It uses a thing called manage beans or mbeans. And then, as I say, you can either manage the application itself or the JVM, and you can do it all from one console. A lot of the standard features you would expect built into this. So there's things like SNMP supported built in, the support for a lot of the standard management consoles, so you can link these things in very easily, and have the idea of being able to say, okay, how much memory is this particular JVM using? What application is running on there? Do I need to monitor specific things about what my application is doing? All of that can be done through managed beans or MX beans in the case of the Java runtime. Number 9, huge pool of developers. Now, there are lots of Java developers in the world. I think we can all agree on that. If you ask certain people, like Oracle, they will tell you that there are 9 million Java developers in the world. Now, I used to work for Oracle, and I have no idea where that number came from, but I think we can all agree that there are literally millions of Java developers in the world. And that means if you're trying to develop new IoT applications, you have a huge pool of talent to draw from. Finding Java developers is not difficult. There are lots of people out there who know how to program in Java. And because you're using standard Java, you're using maybe a different set of libraries to interact with certain parts of the system, it's very easy to find people who understand how to do that. So you're not looking for people with very specific embedded skills or things like that. You can take people who are Java programmers and say, right, write me an application to do this for my IoT system. And, extending that a little bit further, there is a number of surveys that have been done to show just how popular Java is. If you look at the TOB index, TOB actually stands for the importance of being earnest, a book by Oscar Wilde. I have no idea what that has to do with programming, but that's what it is. So there's this company called TOB, and they do an analysis of the popularity of programming languages using various different sources of information. I won't go into all the details of that, but you can see that Java is consistently either number 1 or number 2. In fact, right now it's very much the number 1 popular language, because C seems to be dropping quite noticeably at the moment. This is December's figures that you're looking at here. Similarly, if you look at things like the popularity in programming languages index, they also have Java as number 1. They have Python as number 2. So they use a different way of measuring things. If you look at the RedMonk analysis, that actually is a little bit older. That's January of this year, and so they actually have Java as number 2 behind JavaScript. They only use 2 different values to measure their things. They look at the ranking on Stack Overflow, and they also look at a number of projects on GitHub. And then number 10, of course, powerful development tools. This is really important because you need tools to enable you to be productive. So the great thing about Java is you have a lot of choice. There's obviously Eclipse, which is frequently the most popular development tool. There's IntelliJ. There's NetBeans, which is probably not the most popular development environment, which is a little bit sad for me because I'm a NetBeans user and I used to work for Sun and I used to work for Oracle, so I kind of have a soft spot for NetBeans. But it seems that most people will like either Eclipse or IntelliJ. And the good thing about this is, one, you as a developer have a choice. You're not restricted to having to use one particular tool. If you like one rather than the other, you can use that. These are all available in open source versions. NetBeans and Eclipse are open source. IntelliJ has a community edition, so you can get it for free. And the great thing about this is it takes the grind out of coding. So we have all sorts of things like the ability to do code completion. We don't have to worry about having to look up things. We can have documentation built in. As a developer who's been around for a while, I remember when I started programming in C using VI and make. That was my IDE, because there wasn't an IDE back in those days. And so having an IDE that enables you to do all of these things much, much quicker really does improve your productivity. And it enables developing of IoT applications far faster than if you were using other platforms. So the last thing I just want to mention, because we're talking about running Java on IoT type platforms, is Zulu embedded Java. Now, what we at Azul have done is we have said, right, let's take the OpenJDK source code, and we want to use that so people can run applications on embedded devices. We have ported the OpenJDK code specifically for the Intel architecture and the ARM32. So from a reference board point of view, we use the Intel Galileo, the Intel Edison boards, and we use the Raspberry Pi as our reference for these different versions. The idea here is that we're actually porting these things onto embedded boards, so we know they work, we've tested them. We are a source code licensee of Oracle. We actually have access to the TCK and the JCK. And so we test these builds against the standard, so we know that they work. We provide support for them. And so if you're interested in that, please do have a look at the zulu.org website. So with that, I think I have about 5 minutes now for questions. So I'm going to stop sharing my screen. I can figure out how to do that. And go to questions. Okay.
Thank you, Simon.
Okay.
Great presentation. We have actually a few questions.
Oh, good.
So one of them is, can you talk more about the competition and how Java beats its competitors in the IoT space?
Right, yeah. I mean, I would say that it depends on exactly what area of IoT we're talking about, but primarily what I've tried to talk about in this presentation is comparing it to the traditional native kind of coding. So C and C++, which does tend to be used a lot for embedded programming. In terms of the competition and how do we rate against that, we are certainly seeing a big uptake of Java for embedded projects. I mean, it's difficult to know because obviously we're only one company, but from our experience, because we are specifically supplying JVMs that run on embedded devices, we've seen a lot of interest in that from a variety of customers. Obviously, there's a lot of people still using C and still using C++ because they have specific projects that they build, they have particular platforms that they work on. But certainly for newer type applications, people are seeing the real benefit of Java because of the things I've just explained. The fact that you don't have to continually port applications to new platforms. You port the JVM once, and then you run your application code on top of that. You don't have to worry about moving it and changing things every time you go to a different platform. And that sort of thing is one of the big sort of selling points. So I think that's really sort of showing how Java is becoming a lot more popular on embedded devices at the moment for IoT.
Great. I was wondering if you can turn your camera back on.
Oh, yes, no problem.
Another question is, how small can a device be to run Java on it?
Okay, I think I sort of addressed that, but
well, they're asking like, how small can it really be?
Well, how small can it really be? I think you could get away with 32 megabytes. I've seen people use 32 megabytes as a platform and run a full Java SE environment on there. If you go below that, you're starting to get into more of a kind of Java ME sort of space, because you have to remember that you're not talking about just the JVM running on that platform. You've got to have an operating system as well. I'm going to keep saying we. When I was at Sun, we did have a project called Squawk, which was a JVM that ran on the bare metal. So you didn't need an operating system underneath that, and that would run in a smaller environment. But if you're talking about the Java SE today, you need an operating system. So typically Linux is going to run on top of that. So you need some memory to run Linux as well as the JVM. So I would say 32 megabytes is the absolute bare minimum, and that's going to be a very small application you're going to be running on there. 64 megabytes would be sort of comfortable for running some sort of application that could do a reasonable amount of work.
All right. So what are the JVMs available for the constraints and tiny devices?
So again, as I sort of said, there's Java ME that's available from various suppliers. You can get that from people like Gemalto do that. There's also was it EJ? Can't remember the name of it right now. I had it on my slide, which is a sort of, again, an attempt at making a compressed, smaller version of the JVM. I mean, there's another project I can think of. There's one called Lejos, which is to run Java on the Lego Mindstorm system. Nowadays, the Lego Mindstorm system has a bit more memory, but I remember using it with the very first Lego Mindstorm system, which was only 16 kilobytes of memory on there, and we actually were able to run JVM, sort of. Didn't do garbage collection, and it was a bit restricted, but you could do some fun things with that. So there are some commercial implementations and open source implementations available for very small environments.
I think the name you were looking for was Micro EJ.
Micro EJ, that's it. Thank you. Yes.
They're really good small devices indeed. And so you mentioned Java Card and Java ME. How does it compare to Java as we know it for building classical applications?
Right. So Java ME Java Card is very different because you've got you still got the basic Java language, although it's an older version of the language. You don't have all of the things that you have in like Java 8, so there's no lambdas or stuff like that. So Java Card is very much a different environment because you literally have to take your code and then you have to compile it down into sort of compressed form that will run on the Java Card. But Java ME is a more familiar type of environment because the language is the same. It's Java. Currently, it's based on Java SE7. But you've got a different set of libraries. That's the kind of key difference with Java ME. Is rather than having the full range of Java SE libraries, Java ME has a smaller set. So it's more constrained in terms of what you can do with the libraries. That's the big difference with Java ME. And the way that the JVM works underneath is also different, but that doesn't really affect the application development so much.
All right, and one last question. Do you see JNI being used as a lot to have Java code cohabitating with native C code in constrained IoT environments?
Yes, very much so. I know in a lot of the work I've done with IoT type applications, I've used JNI quite extensively because you often find that there are bits of native code that there isn't necessarily a Java library available for that's equivalent. So what you can do is you can take that Java library and then you can wrap a Java interface around it using JNI so that you can then use that from your application code. JNI is kind of notoriously fiddly to use. And I remember talking to some of the engineers who first designed JNI. And I said, yeah, it's really fiddly because the way you have to do things. And they said, yes, we designed it to be that way to try and discourage people from using it. And it was like, why? But I would say that there are proposals for JDK 10, which will make JNI a lot simpler. So there's this idea of a sort of what called a foreign function interface. So the idea of JNI should get a lot simpler in JDK 10. But yes, for embedded IoT type applications, the use of JNI is a great way of saying, okay, well, I need to get into that low level code that's written in native instructions or native code, and then bring that into the Java side of things so you can use JNI to do that.
Perfect. Well, thank you very much for answering the questions and speaking today. To everyone who's listening, this is our last webinar before the holidays. We'll be back on January 12th with a presentation on Kura wires. You can RSVP for it already. And thank you. Have a great evening, everyone.
Great. Thank you.
Bye.